Um, all right then. So let's continue on with the topic from last time. All right. So last time I was talking about close packing of crystals in 2 dimensions. And I worked out a couple of examples of that. Now I want to scale up to 3 dimensions. So let's begin with that subject in 3D. So I have to share my iPad here. Let's get this going. All right, there you go. As you recall, we were discussing a parameter of the packing fraction. All right, and so there is a packing fraction which is defined as the fraction of the volume that is in particles divided by the total volume. So it's the percentage of volume that is being used effectively for spherical particles, as opposed to the percentage of volume that is being wasted in empty space between the particles. Right. So that's in 3 dimensions. For 2 dimensions, it's a ratio of areas. And so we imagine that for, if we have atoms or other particles with spherically symmetric interactions, that is, non-directional interactions, then we are likely to get a crystal with a high packing fraction. And this is often also called the volume fraction. It's another word that you might hear. Okay, so let's work out an example of how to calculate this. Okay. So suppose we have a simple cubic lattice. So in this lattice, I imagine shrinking the size of the cell down to the bare minimum so that the spherical particles are just touching each other without overlapping each other. Okay. So if we do that, then we get a cubic unit cell, which has some size A. So it's a cube that is A by A by A. And it is made up of spheres, and the radius of each sphere is this distance A over 2. Right? So then we can say, how many spheres are there per unit cell? Okay, well, in this picture, we can see 8 spheres, right? 1, 2, 3, 4 in the front, and another 4 in the back. Right? So there are 8 partial spheres, right? But each of these spheres is only partly inside this cube, and it's partly inside each of the other cubes. So we can ask what fraction of each sphere is inside the cube. And that is like on Monday when we were cutting up slices of pizza. right? But here it's spherical pizza instead. So we could say for a particular sphere, like, oh, the one in this lower right corner, um, we could say it is getting sliced between spheres, sliced into fractions between cubes, right? That are 1, 2, 3, 4 in the back and 1, 2, 3, 4 in the front, okay? And so it is 1/8 of the corner sphere is inside of the cube, right? So we have 8 times 1/8 of a sphere. So that is equal to 1 sphere per unit cell. So the volume inside the particles is 1 times the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. And r in this case is a/2. So that's cubed. So this gives us 4/3 pi a cubed over 8. So that is what? Pi a cubed over 6. Okay. And then we can compare that with the total volume of the cube. It's a cube, which is a length a on each side, so the volume is easy. That's just a cubed. Okay, so the packing fraction then is pi a cubed over 6 divided by a cubed. So it is a pure number, which is just pi over 6, which is approximately 0.524. Okay, that's not so good, right? It's saying that 52% of the volume is actually in the spheres, and the other 47% of the volume is empty space in between the spheres. That's a lot of empty space, right? So a system of atoms with spherically symmetric interactions like this, that's not likely to form a simple cubic lattice, right? There would need to be some other special features of the interactions that would favor a simple cubic lattice. So can we do better than that? And the answer is yes, we can. So here is an example of a structure where we can do better. This is a face-centered cubic, or FCC lattice. And you can recognize that because here we have a sphere at each corner of the unit cell. And then we have another sphere in the middle of each face. Okay? So this is in the front face. And then if we look at the top face, there's 1, 2, 3, 4 spheres on the corners and 1 on the face. Right? And that's the same in each of the faces. So we need to figure out what is the packing fraction for this structure. So for this structure, we need to figure out how many spheres are there per unit cell. Right? So there are both corner spheres and face spheres. Right? And the corner spheres, that you get 1/8 of each corner sphere. And for the face spheres, you get half of each face sphere, because each face sphere is half in this cube and half in the next cube over. And then you have to figure out what's the relationship between the radius of the spheres. Well, that's the diameter of the sphere is d, the radius is d over 2. And how that is related to the edge of the cube, right? And we can tell that because if you go across the diagonal of the face, then you go radius, 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 radius. I will ask you to do this for homework, okay? So on the next homework assignment, there will be the problem to figure out the packing fraction for the face-centered cubic and body-centered cubic structures. Okay? So that's a homework assignment, but I'll just tell you the answer for now. And so the answer is that phi is equal to pi over 3 root 2, which is approximately 0.740. So this is distinctly better than the simple cubic lattice. It's not as good as how we could do in 2 dimensions, but it turns out this is the best that is possible in 3 dimensions. And there are mathematical proofs of that, which I won't go into here. But this is the best possible in 3D. Or to be more specific, this is tied for best in 3D. There are other structures that are equally good in 3D, but there is nothing that is better than this in 3D. So it's a tie for the best possible in 3D. So if you have particles that interact with spherically symmetric interactions, you are likely to get a face-centered cubic, FCC lattice of such particles. Now, one way to understand why this structure is so good in 3D is that we can tilt the structure on its side, right? Either we can turn our heads like this to look at the picture, or we can rotate the picture. So here is the rotated version of the picture, so that a corner of the cube is at the top and another corner is at the bottom. But this is still the FCC structure. And you can see that it has layers when viewed from this angle. All right, that when viewed from this angle, we can see that there's a hexagonal lattice of these sort of olive green colored spheres at this height. And so this is a hexagonal lattice, and we already know that the hexagonal lattice is the best possible packing in 2 dimensions for disks. Okay? So this is making a layer of these olive green colored spheres with the best 2D packing. And then down here, there's another layer of these purple spheres with the best possible 2D packing, right? And so this is basically the way that you would pile up oranges, right? If you own a supermarket, right, and you're making a big pile of oranges, right, you would make one layer of oranges with a hexagonal packing, right? And then you'd make another layer above that, which would also have a hexagonal packing, with each orange resting in between three of the oranges in the lower layer. All right, and so you would make layer number 2 that way. And then you would make layer number 3 above number 2. All right, and then layer number 4 above number 3. In the FCC lattice, you get a kind of repetition where the oranges in layer number 4 are directly above the oranges in layer number 1. And then layer number 5 is above layer number 2, right? So of the 3 sets of positions, it would be going from layer to layer to layer, A, B, C, A, B, C, repeating periodically like that. The other structures that are tied with FCC in packing fraction would have different kinds of alternation, like AB, AB, AB. So this is visualizing one reason why FCC and other related structures are the best possible packings in 3 dimensions. Okay, so this is some geometry. Let me tell you a statistical mechanics side of this. Okay. So let's see, let me add a page. Okay, so suppose we have, whoops, wrong pen. Suppose we have a system of hard spheres. So that means the individual particles are spheres which cannot overlap. Right? So they each have some diameter and they can move around until they are right up against each other. Whoops. Until they're right up against each other like this. But they cannot overlap each other. Right? So that means that there is some interaction between different spheres, a potential energy between spheres I and J. Let's call this number I and number J. And that interaction is 0 if no overlap, and it is infinity if there is some overlap. That is, it would take an infinite amount of energy to make the spheres overlap each other. So they never overlap each other, right? They always have to avoid overlapping each other. This is sort of a simplified version of what we had when we were thinking about the van der Waals theory for the gas-liquid transition. In the van der Waals theory, there's a short-range repulsion like this, and there's also a long-range attraction. Here, there's no long-range attraction. It's only repulsion and nothing else. Okay, so now suppose we try to fit more and more of these spheres into a certain volume. Right? So we are going to increase the density of the spheres and reduce the total volume available for spheres. Okay, so here I have a box. I cram a lot of spheres in this box. then the question is, what kind of phase do we get of spheres in the box? This is an unusual kind of problem because the interaction is so simple, right? And the interaction doesn't even have an energy scale. The interaction is just 0 or infinity. The remarkable thing is that this system actually crystallizes. It crystallizes for a high enough density, rho, or a low v, the volume per particle. Okay, and so this system, even though it is this simple, has a crystallization transition. The crystallization depends on density or on the volume per particle. It does not depend on temperature. Temperature doesn't really matter here because there's no energy scale for the interactions. The interaction is just this 0 or infinity thing with no temperature involved. So there's a sort of phase diagram for this system, which is a one-dimensional phase diagram because it only depends on one variable, which is the density. So I'll make a one-dimensional phase diagram like this, with density as the only axis. Well, I could use density, but instead of using density, what people usually do is think about packing fraction instead as the axis here. And so you could convert density into a packing fraction by saying the packing fraction is the volume in particles divided by the total volume. And the volume in particles is the number of particles times the volume of one particle, okay, divided by V total. And then the number of particles divided by V total, okay? Well, this is the density of particles per volume. You might call this the number density or the concentration of particles per volume. It's not the same units as the mass density, but it's related to the mass density by a factor, which is just the mass of one particle. And then this is multiplied by the volume of one particle. So if I want, I could express the phase diagram in terms of this phi instead of in terms of this density of particles per volume. Those are two equivalent representations, which are just related by this factor, which is the volume of one particle. So let's draw the phase diagram in terms of that phi. Okay, so here this is phi running from 0 to 1. Okay. And the phase diagram that is found by computational research looks like this. Okay. So I'll mark off a couple of special points, 5, 4, 5, 0.740. Okay, so for this system at low density or low volume fraction, less than 0.494, we have a liquid of hard spheres, right? Some disordered phase of hard spheres.
Excuse me. I think it would be better to call it fluid than calling it liquid, because there's no gas. There's no difference between gas and liquid. There's no gas-liquid phase transition. So
that's a good point. What Cheng is pointing out is that if we remember how things were in the van der Waals theory, right? That we need both the parameters B and A to get a transition between liquid and gas. Okay? And this simplified system has B, it has some minimum volume, but it doesn't have an A. It has A equals 0. So we could go back to the results of van der Waals theory and say, oh, when A equals 0, the critical temperature is 0. We're always past the critical point, right? Any system is past the critical point. Okay, so past the critical point, there is no difference between gas and liquid. Right? So nowhere on this phase diagram is there a gas-liquid transition. So we could just say liquid equals gas equals fluid equals supercritical fluid. Those things are all the same. So Cheng is saying, wouldn't it be better to use the word fluid as a general term that could describe both liquid and gas? Yes, it would. So from that kind of rigorous point of view, Cheng, you are correct. The fluid would be a better word. From the point of view of what people actually say when they're talking about crystallization, right? When people talk about crystallization, they normally talk about the transition between liquid and crystal. And so they refer to the disordered phase as a liquid. But that's sort of a point about sociology. That's not really a point about science, right? And so you are absolutely correct that these are all correct descriptions of what's happening in that phase. And that fluid would be a nice general word to use. We could use any of these words.
Okay.
Excellent point. All right, what was I saying? Oh, yes. So this phase, whatever we call it, is what occurs in a range of volume fraction from 0 to 0.494. So it could occur at very low densities, way down here, you would see something that looks very much like an ideal gas. Okay. At higher densities, as you go up here, it would be an interacting gas or a liquid, but there'd be a, a fair number of particles per volume. Okay. Now, remarkably, when you get up to a larger range, up here, in this range, between 0.545 and 0.740, there is a crystal phase. Right? That is that the hard spheres can spontaneously form a crystal, an FCC crystal to be more specific. And so at the highest point, at the 0.740, they form an absolutely close packed crystal where they are crammed in as densely as they can possibly be, touching against each other, pushing against each other. At the lower range, if you're down here somewhere, well, then it's a crystal with a little bit more space. There's a little bit of breathing room. There's a little bit of room to vibrate there. So the atoms can move around a little. I'm kind of exaggerating that in this picture, but the atoms have a little bit of room to move around. They're not totally packed in, pushing against each other, but they do form a crystal so that you can identify special positions and special directions, right? It is a crystal which is non-uniform and anisotropic. So there is a sequence of special positions, here, 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 right? And a sequence of special directions, which are the rows and columns of particles. Beyond 0.740,
Jonathan,
question, Bajaya.
okay. Uh, Let us assume we have a water and ice, and between the, before reaching to crystallization point, there will be no change in density almost. So there will be no change in packing fraction. Density is almost same.
Yeah, let's not talk about ice just now. I'm going to postpone that question for
Okay.
a minute. Okay. This is for the specific case of hard spheres, which water molecules are not. Water molecules are a lot more complicated than
Okay.
that. For the density beyond 0.740, this is just impossible. It's impossible because I already told you that this 740, this is the maximum you can get for packing fraction in 3 dimensions. Anywhere beyond that, you would need to have the spheres overlapping each other. And I already made the assumption that it would take an infinite amount of energy for the spheres to overlap each other. So that will never happen. Okay? So it's impossible out here. Now, what you are all wondering is, what about in this range, right about there? It's not liquid, it's not crystal. Right? You could say it is a range of density which is bigger than the maximum density of the liquid and smaller than the minimum density of the crystal. Okay? So this is a range where there must be two-phase coexistence. Like the coexistence of two phases that we've dealt with before in the midterm exam and in the one of the previous homeworks. Right? And so anywhere in this range, the system can't be pure liquid or pure crystal. Instead, it has to be some liquid and some crystal. So it'll be a combination of some liquid with this density and some crystal with that density. And if you wanted to know how much liquid and how much crystal, you would need to solve the 4 equations and 4 unknowns, right? To get something like the lever rule. So if you're very close to here, it's mostly liquid. If you're very close to here, it's mostly crystal. And in between, there are different ratios of liquid and crystal inside the material. Now, I'm not deriving this for you. I'm just telling you the results of simulations and calculations that people have done, as well as experiments on systems that are similar to hard spheres. There's no such thing as exact hard spheres in experiments. There's always some slight corrections to that, but systems that are approximately like that in experiments. Now, please.
I just want to make sure I understand this diagram correctly. Is the reason why there's no temperature dependence here that the interaction between spheres is hard sphere interaction?
Yes, exactly. So that the energy is either 0 or infinity, right? That's this assumption right there, okay? So that means that whenever you have a Boltzmann factor, that's like e to the minus energy over kT, right? Either you have e to the minus 0 over kT, or you have e to the minus infinity over kT. Right? And so those factors are either 0 or 1, and they don't depend on temperature, right? And so because the 1 over kT is always multiplied by either 0 or infinity, temperature is not important.
Mm-hmm.
So whereas if there were any characteristic energy scale, then you would have to say, well, how does the temperature compare with that characteristic energy scale?
Mm-hmm.
And so that's why there's no temperature dependence in this, system. Okay, Ibrahim, you had a question?
Yeah, we consider here the overlap is organized or not organized, because sometimes when the overlap happen and the solid formed, this solid might be amorphous or might be crystalline. So here we take only one case, is the crystalline one. Am I right?
That's right. So here I'm only speaking about thermal equilibrium, where
Yeah.
there is a crystalline phase. The amorphous possibility is metastable, which I'll be talking about later in a few days.
Yeah, thank you.
Great. Now, let me point out to you something which is a little bit surprising about this system, okay? And it goes back to the point that we were just talking about with the interaction, that it is 0 if no overlap and infinity if there is overlap. Okay. Let's think about the free energy, okay? Because I've been trying to present everything to you in the context of free energy in this semester. So we know that the free energy is this average energy minus temperature times entropy. In this system, right, the average energy, this is averaged over all the possible states that can exist, okay? So the states that can exist, that's only states with no overlap, because if there were any overlap, that would be forbidden, right? That would cost infinite energy, and so it couldn't happen. Okay. So if you take the average over all the states that can happen, that's an average over states that have no overlap. So they have zero energy. Okay. So this average energy is zero. So the free energy is just minus temperature times entropy. Right? That this system just has entropy and not energy, right? So the phase transitions are entirely controlled by entropy, right? With this factor of negative temperature, which is just a constant multiplying the entropy, a negative constant multiplying the entropy. Right? So if we want to minimize F, right, we do that by maximizing the entropy. Okay, it's just entropy. This is a little bit weird, right? It is a little bit weird because normally we think in most phase transitions, there's like a fight between energy and entropy, right? In most phase transitions, energy favors the ordered state and entropy favors the disordered state. And so at a certain temperature, there's a balance between those things and we have a transition, okay? But here, there's no energy, it's only entropy, okay? So you might think for that reason that the system would never have an ordered phase, right? You might think it would always be disordered in a liquid or a gas, right? And that's actually what people thought for a long time, okay? But weirdly, that is not true. Weirdly, this system with only entropy still has an ordering transition, right? It has a crystallization that is driven entirely by entropy. And let me try to make a sort of cartoon that illustrates why that would be true. Okay, the point is that entropy, well, you could say there are different forms of entropy. Okay, there is some long-range entropy, which means no order of positions or directions. That's the entropy that we usually think about. Right? But there's also a kind of short-range entropy for the particles. And that is that we want room for the particles to vibrate around. That is, there's entropy associated with the particles to be able to just move back and forth a little bit so that they have a lot of little range of positions, which we would hardly notice from a macroscopic scale, but still it's important to them, right? They want to have a little bit of elbow room where they're not just pushing right up against their neighbors. Okay. So if you have a liquid phase, then the particles, here I'll draw them smaller than that. If we have particles that are not packed in an efficient lattice, then they're likely to just kind of push up against each other and limit the room to vibrate just because of not being packed very efficiently, right? But if you have the same number of particles in a crystal phase in the same volume, I'll try to draw it like this. Because this is supposed to be the same number of particles in the same volume in these two pictures. It's not the greatest picture I've ever drawn, but it's something like that. Okay, so the point is, because these are organized better, right, then each of the particles has more room to vibrate around. Okay, and so that consideration by itself can give a higher short range entropy for the crystal, even though the liquid has more disorder of the directions and positions. And so we might say then that the crystal is favored by the short range entropy of vibrations, whereas the liquid is favored by the usual long range entropy.
Excuse me. Can
Uh-huh.
I say that the short range entropy dominates when ergodity disappears? Because for crystals, particles cannot move around in the whole available space of the material, right? It can only be localized around a certain small.
True. I would say, I mean, this is a description of an equilibrium phenomenon, right? That the balance between these things is part of equilibrium, you know, and it's established by you know, by simulations and theoretical calculations that are explicitly assuming equilibrium. So the story that I'm telling about long and short range entropy, this is one of these hand waving stories where I kind of try to make up an intuitive interpretation for the real calculations. Okay? But there are real calculations. I'm not showing them to you, but they exist. Okay. And so this is a feature of real calculations. And here is a way to sort of interpret how could those calculations possibly be true, even though they sort of violate our intuition about what entropy ought to do.
Okay.
Okay. The reason why I am making a big deal about this is that in a few weeks, we will see something similar to this in liquid crystals, right? In a system of liquid crystals with hard interactions where entropy does a surprising thing. And I will at that point say, oh, remember the crystallization of hard spheres. This is sort of similar to that. All right, how am I doing on time? I am about out of time here. Okay, I will stop talking here, and in the next class, I will move on to a different subject related to solids, right? So you remember I told you previously that there are some solids which are distinguished by their mechanical properties, not by regular order of crystalline positions and directions. And so in the next class, I will begin with talking about what are the mechanical properties of solids compared with liquids. So how do we distinguish them? And then we'll go on to amorphous solids, right? The solids without crystalline order. Okay, so that will be on Friday. So I'll see you guys then. Thank you.